Jai Hind. We are continuing our discussion about electric potential. We have the expression for electric potential V equal to infinity to R, integral infinity to R E dot dr, and the potential difference is given by delta V equals integral, the final point is B A and the initial point is B, and hence we can integrate B to A E dot dr. From the two formula we can write the unit of potential or potential difference as electric field. Electric field is Newton per coulomb and the distance dr is meter and hence Newton meter per coulomb, and where Newton meter is joule and hence joule per coulomb is called the volt. Therefore, the unit of potential or potential difference is volt, and potential is considered to be a scalar quantity also. Potential is a scalar quantity. Clear? Now, the potential and potential difference, if you see the formula, here it is integral B to A, or here the integration from infinity to R. That means the work done. So, what is the definition of potential or potential difference? It is the work done in bringing uniposity charge from infinity to a point, that is potential, one point to another point, that is potential difference. So, if the charge is taken from one point to another, or the charge is taken from infinity to a point, if you consider the same example, if a charge is here and if the 2 points A and B are here, we can bring the charge, uniposity charge from B to A, okay, or infinity to A through the straight line path, through this path, or we can take the charge from B to A along this curve path, or we can take the charge along another curve path. Through any path we can take the charge. So, whatever be the path taken by the charge, it depends only on initial point and the final point. Okay, so the work done in bringing a uniposity charge from infinity to a point or one point to another does not depend on the path through which it is travelled. It depends only on the initial and the final point, and hence electrostatic force or Coulomb force is a conservative force. Okay, and hence the work done in moving the charge, uniposity charge from one point to another or infinity to a point, the work done does not depend on the path through which it is traversed, and it depends only on the initial and final point, and hence electrostatic force or Coulomb force is said to be conservative. Okay, last year in 11th standard we have studied what are conservative force and what are non-conservative force. So, here electrostatic force or Coulomb force is conservative. Clear? Now, if a graph is plotted with the electric field or potential along the y-axis and distance along the x-axis. So, what is the variation of distance and with electric field and potential? Okay. So, again in the last chapter we have studied what is the formula for electric field. E equals 1 by 4 pi epsilon 0 q divided by r square. Electric field at a point due to a point charge, and potential is given by 1 by 4 pi epsilon 0 q divided by r. This is the formula for potential due to a point charge. So, what is the relation between them? One r is missing here, no? In potential one r is missing. So, we can write, comparing these two formula, we can write electric field E is equal to V divided by R. This is a very important expression. Electric field at a point due to a point charge, that is E, and potential at a point due to a point charge, that is V, and hence the relation between them is E equals V divided by R. So, from the formula we can write another unit of electric field. So, in the last chapter we have the unit of electric field is Newton per coulomb. In this chapter another unit of electric field can be defined. Another unit of electric field is potential difference, volt, or potential volt per meter. Okay, so volt per meter is also another unit of electric field. Clear? Now, come to the graph. So, if a graph is plotted with distance along the x-axis and electric field and potential along the y-axis. So, here electric field is inversely proportional to r square and potential is inversely proportional to r. Okay, so here the graph, if a graph is plotted, electric field, this will be the graph. As distance increases, electric field decreases very sharply. But potential difference or potential, the change in potential is not as much sharp. Okay, so since the electric field is inversely proportional to r square, this will be the shape of the graph, and since potential is inversely proportional to r, this is the graph. Okay, so both are inversely proportional, but electric field decreases sharply, okay, steeply with r, because it is inversely proportional to r square. So here this represents electric field, and this one represents potential difference or potential. Okay. Now one more point to be added, and we have the potential due to a point charge is V equal to 1 by 4 pi epsilon 0 Q by R. Now we can write what is the potential due to system of charges. Potentially at a point due to system of charges. So if number of charges are there, for example, plus Q1, plus Q2, plus Q3. Okay, let 3 charges are there, and here is the point P. This distance is R1, this distance is R3, this distance is R2. Okay, so consider a system of 3 charges Q1, Q2 and Q3, and the distance between the charge and the corresponding point is R1, R2 and R3. We have to find out potential at the point P due to these 3 charges. So first we can write the potential at the point due to Q1. So that is V1 equals 1 by 4 pi epsilon 0 Q1 divided by R1. That is from the formula. Okay. Potential at the same point due to second charge Q2 is V2 equals 1 by 4 pi epsilon 0 Q2 divided by the distance R2. And again the potential at the point P due to Q3 is V3 equals 1 by 4 pi epsilon 0 Q3 divided by R3. And hence what is the total potential or what is the net potential at the point P due to all the 3 charges is, take the algebraic sum, that is V1 plus V2 plus V3. Okay, so it is equal to 1 by 4 pi epsilon 0 can be taken common, and hence it is Q1 by R1 plus Q2 by R2 plus Q3 divided by R3. So that is a net potential at the point P. Take the algebraic sum. If any charge is negative, we have to put negative sign here. If Q1 is negative, let Q1 is negative, put negative sign. If Q2 is negative, then also we have to put negative sign. Since potential is a scalar quantity, no need to consider the direction. Just put positive, negative for the corresponding charges. So it is an easy method. Okay, but in electric field, we have to consider the direction also. Okay, while finding the total electric field. But here, since potential is a scalar quantity, just find out the algebraic sum. Okay, so hope you understood all these important points. Okay, thank you.